All right, let's talk about the Unit 3 practice test. So it's helpful to have the common polyatomic ions and the periodic table nearby. For number 1, however, though, this is really reviewing our understanding of what makes up each type of the bonds. So we need to do some matching here. So if something has ionic bonding, it's made of a metal and a nonmetal atom. If something has covalent bonding, there's two types. There's molecular covalent bonding, and there's also network covalent bonding. These are both made of all nonmetals. So how do you tell them apart? The molecular covalent are typically gases, liquids, and sometimes they're solids. But if they're a solid, then they're a soft solid or they dissolve in water kind of solid. Versus network covalent is a very hard solid. And then finally, there's metallic bonding, which is made of all metal atoms. So that's how you tell the difference between the types of bonding. So for this first one, gold 3 chloride, we look at the locations. So to the left of the zigzag, we have gold, and to the right of the zigzag, we have chlorine. Anything to the left of the zigzag is a metal, and anything to the right of the zigzag is a non-metal. So the answer would be gold 3 chloride. That would go with the ionic bond. The next one, H2o gas, is water, so steam, this should really say. And hydrogen, although it's to the left of the zigzag, it's still a nonmetal, and so is oxygen. So since they're both nonmetals, we know it's covalent. So then we have to decide, is it molecular or network covalent? Well, molecular covalent is the ones that are gases, liquids, and sometimes solids. So this would go with molecular covalent. Then we've got copper. Copper, which is located right here to the left of the zigzag. So that would be a metal. And since it's just metals, it has metallic bonding. And then the last one, silicon and oxygen are both on the nonmetal side. Silicon's actually a metalloid, and there's some mention of this in the notes too, that metalloids are often in network covalent bonds. So this one would be network covalent. Match each type of chemical bonding with its properties. So this is just kind of thinking of that pivot lab that we did and the lab that I did in my kitchen. And I like to recommend thinking of an example of something that has this type of bonding before you try to match it with its properties. So something that has molecular covalent bonding, that's a common substance, is sugar. Metallic would be copper, like a copper penny. Ionic would be salt. And network covalent would be something like sand. So one of these, only one, has a low melting point. And you might remember that sugar on my stove dissolved easily. And molecular covalent things are sometimes soluble. Sugar did not conduct as a solid, and it did not conduct as an aqueous solution. Right? For metallic is the only one that's conductive as a solid, and they're not soluble. So that would be a match with copper and metallic bonding. And then salts, you can think of, it does dissolve and it conducts as an aqueous solution. So salt would go with this top one. It conducts as an aqueous solution. And last but not least, sand, network covalent, is the boring one. It doesn't melt, it doesn't dissolve, and it doesn't conduct as a solid. Which noble gas would nitrogen most be like? So if we go to number 7, nitrogen, it's closest to number 10, neon, right? Because it's 5 away from helium, but it's only 3 away from neon. So the answer would be number 10, neon. Which of the following would conduct electricity when dissolved? So metals don't dissolve. Silver is a metal. And let's look at our other ones here. This one has molecular covalent bonding because it's a gas. This one is sugar, and it does dissolve. It's all nonmetals, so it's a molecular covalent. And KCl, that's a metal and nonmetals. That would be ionic. So ionic bonds do conduct electricity when they're dissolved. So that's how we can figure out that that first one is the answer. Again, because if you aren't quite sure, you can look up K and see that it's to the left of the zigzag and Cl is to the right. And so when you've got a metal and a nonmetal together, that's ionic. For the next one, it says match each element with the appropriate number of electrons it wants to gain or lose. So if we go to neon, neon is number 10. It doesn't want to gain or lose anything because it's already in the perfect group, the noble gases. So neon wants to gain or lose 0. Phosphorus is right here. It would like to gain 1, 2, 3 to be like argon. So phosphorus would like to gain 3. Sodium is right here, number 11. It's very close to neon, number 10. So it would like to lose 1 to be like neon. Magnesium, number 12. It's only 2 away from neon, so it would like to lose 2 to be like neon. Sulfur, number 16, is 2 away from argon, so it would like to gain 2 to be like argon. Fluorine is, this is kind of getting messy, it's only 1 away from neon, so it would like to gain 1. Carbon is right in the middle, number 6. It could either lose 4 to be like helium, or it could gain 4 to be like number 10, neon. So it would like to gain or lose 4. Did I do this one to the wrong one? Magnesium would like to lose 2. I think my arrows got off somewhere along the line. Here we go. And then aluminum, last but not least, aluminum's number 13. If it loses 3, it will be like number 10, neon. So aluminum would like to lose 3. Without oxygen, we would not be able to live. Write the symbol for the oxygen, or for the ion oxygen will form. So oxygen would like to gain 2 electrons to be like neon and form a -2 charge. So the symbol would be O2-. Element X is a metal that would like to lose 2 electrons to be like a noble gas. Element Y is a nonmetal that would like to gain 2 electrons to be like a noble gas. Which of the following shows the correct ratio between the atoms? It would be 1 to 1 because their charges cancel out. So they're a perfect soulmate match. Lithium oxide is a very corrosive compound. Draw a picture of the valence shells and the transfer of electrons in the formation of the ionic compound between Li and O. So Li is in group 1A, so that means it has 1 valence electron. Oxygen is in group 6A, So it has 6 valence electrons. So lithium, 1, oxygen, 6. So lithium would really like to lose 1 to be like helium, and oxygen would really like to gain 2. So 1 lithium is not enough for an oxygen. You need 2 lithium atoms to satisfy 1 oxygen. How would you name MgBr2? First step, figure out, is magnesium a transition metal? No, it's not. So we would start by naming it magnesium, and then we would not name it bromine because we would change the ending to be "ide," magnesium bromide. For a monatomic ion, you always change the ending to "ide." For number 10, we've got a polyatomic ion, Al2CO3 Okay, we know Al's name is aluminum from the periodic table. And then there's this special polyatomic ion, CO3. Its name would be carbonate. Aluminum is not a transition metal, so it does not get Roman numerals. But number 11 is Fe. It's a transition metal. So we've got to figure out what its charge is. It's bonded with 2 fluorines. Fluorine wants to gain 1 to be like neon. So each one of these will have a -1 charge. So in order to cancel out a -2 charge, iron must have a +2 charge. So this one's name would be iron Roman numeral 2 fluoride. And then this one, type the chemical formula for sodium phosphate. Sodium has a +1 charge according to the periodic table, and phosphate on the polyatomic ions has a -3. So when you crisscross the charges, you get Na3PO4. And last but not least, this one says you've got chromium with a +3 charge, sulfide, which has a -2. So this would be Cr2S3. Cr2S3.